Wilczek, che è qui con noi. Frank Wilczek è... Grazie. Hermann Feshbach, Professor of Physics all'MIT di Boston. Ha ricevuto nel 2004 il premio Nobel per la fisica per la scoperta della libertà asintotica, che è un aspetto chiave della comprensione delle interazioni forti in fisica nucleare. Questa scoperta, nel 1973, è stata descritta in un'elegante formulazione matematica che ha condotto allo sviluppo di una teoria completamente nuova, che è conosciuta con il nome di cromodinamica quantistica. Questa teoria, che si è sviluppata in questo nuovo quadro concettuale, risulta essere una teoria che ha una straordinaria bellezza formale e, molto importante, in termini quantitativi un notevole e importantissimo potere predittivo, che è stato confermato dagli esperimenti dei grandi acceleratori negli ultimi 15 anni. Tra l'altro con un'accuratezza decisamente sorprendente, a pochi punti percentuali. Questa teoria ha guidato la ricerca sperimentale nella fisica delle alte energie, ha consentito fra l'altro di avere per la cosmologia un quadro di riferimento che ha consentito di affrontare lo studio dei primi istanti dell'universo e inoltre ha posto le premesse per realizzare il sogno dell'unificazione delle teorie che descrivono le forze fondamentali della natura. L'attività scientifica di Frank Wilczek, che ha dato contributi non solo alla comprensione della forza fondamentale della natura, ma anche alla fisica delle particelle, alla cosmologia e alla fisica della materia condensata, ha ricevuto un numero straordinario di riconoscimenti, che non elencherò perché sono impressionanti. Last but not least, Frank Wilczek è anche l'autore di sonetti, uno dei quali, Virtual Particles, sono dedicati alla fisica delle particelle, ha avuto l'onore recentemente di entrare in un'antologia che si chiama Northern Anthology. No, non aggiungo altro. E quindi voglio dare la parola a Frank Wilczek, che ci parlerà oggi della ricetta numerica del mondo.
Thank you. It's lovely to be here in Rome, where so much great in science and physics has occurred, and where antimatter from CERN became the plot of a great novel, Angels and Demons. I'm going to speak tonight about how to make the world out of numbers, which is a great achievement of modern physics, still incomplete. Modern physics really began, I think, around 550 BC, when Pythagoras made a great discovery that connected mathematical relationships to physical realities, and announced, based on this, an awesome vision of what science could achieve. What he discovered was that the sounds which sound good to us, that are harmonious, that sound well together, are the sounds that are emitted by strings that are under equal tension and of the same kind, if their lengths are in simple numerical ratios. So if the length of the strings that you pluck is 2 to 1, it sounds an octave. If it's 3 to 2, it sounds a fifth, the dominant, which also sounds good. 4 to 3 is a little more dissonant. That's the fourth, sometimes called the devil's tone. And 5 to 4 is the third. In any case, these are the basis of harmony in music. This discovery to this day is not really understood, why those things sound good, but they certainly do. And it was a fantastic relationship showing that purely numerical quantities can describe surprising things about the world. Based on this, Pythagoras made a gigantic leap of imagination to the concept that all things are number, that every aspect of reality somehow reflected numerical relationships. A modern form of this is more general. We have a more general concept of numbers, that they are concepts, logical constructs we also count as fair game for constructing the world. As Professor Sen emphasized last night, we should be inclusive in our concepts and let nature tell us what concepts we should use. But a great discovery of 20th century mathematics is that all logical concepts can be expressed in terms of zeros and ones, if you have enough of them. And so now the program getting all things from number becomes the program of getting its from bits. And I'm going to show you tonight how far we've come in that program. I'm going to show you in the first part of this lecture how we can construct ordinary matter or normal matter, the stuff that you and I are made out of, using a theory that's based on pure concepts plus 2 numerical inputs that we have to take from experiment, exactly 2. Well, actually, that's a slight lie, which is why I put this in quotation marks. That theory is only a very good approximation to reality, as I'll describe. If you want to get a really accurate theory, it takes 4 numbers. And if you want to extend your theory from Earth to astrophysics, to the cosmos, you need 2 more numbers, and it's 6 altogether. The concept that you could describe physical reality using pure numbers inspired many people after Pythagoras, and perhaps reached its culmination temporarily in the work of Kepler in the 16th century. He, as Professor Glashow alluded to, was inspired in astronomy by the idea that he could relate the sizes of different planetary orbits to the shape of regular solids. So he inscribed and circumscribed regular solids around spheres, which were supposed to carry the planets. Today we study Kepler's 3 laws of planetary motion, but this was the 0th law of Kepler's system of astronomy, which really got him excited about astronomy and which he saw as a great contribution. We don't study it anymore for the very good reason that it's wrong, but it inspired him, and in his whole career was longing for the harmonies that were expressed here. He even thought that as the planets move around, since their motions are periodic, they would be emitting musical tones, which are, after all, are the reflection of periodic vibrations of musical instruments. And he even somehow, I've never figured this out myself, managed to write down exactly what the planets were singing. But Kepler's 3 laws that followed his first 0th law really destroyed the 0th law. If the planets move around in ellipses, which is what he discovered, they can't really fit into a system like this. It's lopsided, and the things can't slide around each other. And Kepler was an honest man, so he reported those laws nevertheless and gave up his fondest dreams. And really, that led to Newton's mechanics. And in Newton's mechanics, the Keplerian ideal that you would explain everything about the world in terms of pure concepts, of pure numbers, was abandoned. In particular, this idea that you would figure out the shape of the solar system from pure concepts was abandoned. In Newtonian physics and in reality, you can have solar systems of different sizes and shapes consistent with the basic laws. And nowadays, astronomers are in fact finding distant solar systems with different sizes and shapes. So in classical physics, this concept that you could get a unique conceptual description of matter really doesn't work. And that's where it stood for 250 years or so. That inspiring vision went into eclipse. It came back, however, in the 20th century, really starting with the work of Niels Bohr around 1912. Einstein called this work the highest form of musicality in the sphere of thought, both because it's extraordinarily powerful and an insight into nature, but also quite specifically because it brings in to physics concepts that, into atomic physics, concepts that previously were used in describing sound and music. Bohr's model of the atom was very much like a solar system, except that the orbits are now, unlike a Newton system, not allowed to have any size and shape. Bohr gave rules, the so-called quantum rules, that said only certain sizes and shapes of orbits are allowed. So these were mathematical rules that determined that you couldn't have any old size or shape, that in fact pure concepts ruled the possible sizes and shapes and forms of hydrogen atoms. This could be checked experimentally because as atoms of hydrogen absorb light, making these black bands in a spectrum when you shine light through hydrogen gas, the energy the energies that are absorbed are the energies that correspond to the energy absorbed as you move from one of these orbits to the other. So if you can predict the energies, you can predict what kinds of light will be absorbed. The relationship between the energies and the frequencies of light is the Planck-Einstein-Schrödinger relation, E equals Planck's constant times the frequency. Please don't be frightened by this formula, but this is in more detail the formula for the different energies that you can get as you have transitions between different orbits in hydrogen. The orbits are labeled by whole numbers, by integers, and now I'm going to deconstruct this formula. Whoops. If my computer will cooperate. See, I'm sorry, the pointer doesn't do the same thing as... well. Stop there. Good. These numbers that appear in the formula for the physical behavior of the hydrogen atoms are, by any account, purely conceptual numbers. They're whole numbers here, and whole numbers can be described by pure logic, by counting. You don't need to do experiments to say what a whole number is. Pi also is a pure number that you can define purely conceptually. You don't have to actually measure circles. You can calculate what the ratio of the circumference to the diameter is, and there are numerical formulas for it in terms of whole numbers. So those are explicitly realizing the Pythagorean vision of getting reality in terms of numbers or pure concepts. Deconstructing this a little more, whoops. Planck's constant, h, we saw before. Okay. I'll try once more. All right. Remember this. H is what I call an honorary number, because it appears as a conversion factor in that Planck-Einstein relation, E equals h nu, that's necessary in describing the basic principles of quantum mechanics. There's a unique relationship between the energies of quantum mechanical photons and the frequencies of the light they represent, but energy and frequency are measured in different units, so to make sense of the law, you need a conversion factor, And in that law and many of the other laws of quantum mechanics, h appears as the necessary kind of unit or conversion factor. So since it's necessary in the formulation of basic laws, I call it an honorary number. And then finally, sorry, it worked before. There are two other ingredients of these formulas that are not conceptually defined, but have to be determined by experiments. This is a number alpha, which is roughly 1 over 137, but not exactly. It's something you measure experimentally, called the fine structure constant, which sets sort of the overall scale of these frequencies. And then there are the masses of the electrons and protons that also appear. This formula simplifies. Terribly sorry about this. This simplifies in reality because the mass of the proton is much bigger than the mass of the electron and becomes simply the mass of the electron. So to summarize, this description of the structure of the hydrogen atom, of its different orbitals, and of the different kinds of light that it absorbs, is given in terms of purely conceptual numbers plus two ingredients, the fine structure constant and the mass of the electron. And this analysis, which I've shown in terms of the original Bohr model of hydrogen, holds up in modern quantum mechanics too, in the Schrödinger equation. You can describe everything about not only the hydrogen atom, but hydrogen molecules, more complicated molecules, their sizes and shapes, the kinds of light they emit and absorb, to a very good approximation using only concepts and these two measured quantities, the mass of the electron and the fine structure constant. For experts, I'll say that there are two honorary numbers involved, the speed of light and Planck's constant as well. So you get a tremendous amount from very little. All of structural chemistry, all of photochemistry is encoded in just these, in pure concepts and these two numerical inputs. However, that theory, remember, that simplification involved taking the proton mass to infinity. If we want a more accurate theory, we have to let protons have a finite mass. This theory, although it explains a lot, the sizes and shapes of molecules, doesn't allow anything to move other than electrons. Okay. So to get a more accurate rendering of reality, we have to recognize that atomic nuclei, the things at the center of atoms, protons for hydrogen and more complicated things for other kinds of atoms, also need a theory. And until the early 1970s, there was no conceptually based theory. There was no deep theory at all about how to make atomic nuclei. People had a rough idea that you could assemble protons and neutrons, put them together, and they would stick and make nuclei. But as people investigated protons and neutrons in more detail, trying to understand what the nature of the forces between them was, or is, and what protons and neutrons themselves are, they found that these are actually extremely complicated objects. The more you studied them, the more complicated the equations you needed to describe their behavior. So that was very disappointing. However, we learned that there is simplicity, just one level deeper, that protons are made out of things called quarks and gluons, and that these do obey simple equations. These are simple. Now, I said simple with a capital S. That doesn't mean simple in the usual way of something you can immediately grasp without thinking hard about it. But it does mean something that doesn't require a lot of logical input. If you have a very powerful computer that can carry out complicated logical operations, you could give it a short program which told it everything there is to know about quarks and gluons. That's what simple with a capital S means. So not necessarily simple for humans, but simple for ideal thinkers. Let me describe this theory, at least metaphorically, in some more detail. So it's called quantum chromodynamics, or QCD. For normal matter, that is the matter that you and I are made out of, that we study in chemistry and biology and material science, the only important quarks are two kinds called up and down quarks. They come in each of them comes in three varieties that are called different colors of quarks. But these colors have nothing to do with how the quarks actually look. They're not actually the color of anything. The wavelength of light is gigantically large compared to the size of a quark, and they don't correspond to any color, so they don't actually look like this. The colors are actually more like electric charges. The different kinds of colors are different kinds of charges, and this whole theory kind of looks like electricity and magnetism, but on steroids, beefed up, bigger, using the same concept, but in a mathematically richer structure. Instead of one kind of charge in electricity and magnetism, here you have three kinds of charges. And whereas in electrodynamics, you have one kind of photon that responds to charge and mediates the electric and magnetic forces, in this bigger and better theory, you have 8 different kinds of photon-like particles, which are the gluons. But the big message is not the details, but that this theory deeply, at the basic mathematical level, looks very much like the theory of electrodynamics, and that suggests possibilities for unified description, which we'll come to in due course. Here are the equations in pictures. The equations just tell you that different kinds of gluons respond to other different kinds of gluons, and for every possible combination of the 8 gluons, there's a number telling you how strong each one couples to the others. And the gluons also can be exchanged between quarks, and similarly to how the exchange of photons or electric fields gives a force between electrons, the exchange of gluons gives a force between quarks. And really, although I'd fail a graduate student for saying this is quantum chromodynamics, it actually is an honest representation of the content of the theory. By knowing these basic couplings of the gluons to the quarks and to each other, you know everything there is to know about the theory. Here's the real thing. You can write it down on one page. I won't insist on the details. Just a couple of things to note. These F's are numbers. The G's are the gluon fields. The F's are the numbers which tell you how strongly the different gluons couple to each other. And the T's are things that tell you how strongly the quarks couple to the gluons. And the structure of the theory is such that the F's and the T's are completely uniquely determined. So they're determined purely by symmetry, purely by concepts. The only non-conceptual ingredients in defining the theory are a mass for each kind of quark and an overall coupling constant. So it's simple in the sense that if you told a computer about the symmetry and fed it just 2 non-conceptual quantities, or I'm sorry, 3 at this point, non-conceptual quantities, it would be able to compute everything about the consequences of this theory, and therefore, as we'll see, everything about atomic nuclei, their masses, what kind exist, and so forth. You shouldn't be too impressed by the fact that you can write down so much on one page in simple-looking notation. Richard Feynman was able to go much further. He found an equation that describes everything in physics, all the laws that have ever been discovered, and all the laws that ever will be discovered, not only in one page, but on one line in a definite equation. And here's the equation, u equal to 0. Of course, I have to tell you what u is. U is something called the unworldliness. And the unworldliness of the world is the sum of different kinds of unworldliness. So, for instance, one contribution to the unworldliness of the world, we can call it the Newton's second law unworldliness, is F minus ma squared. Another contribution from electrodynamics is the Gaussian unworldliness of electric charge, and for experts, that's del dot E minus rho, all squared. And so on. You take all the equations of physics, square them, each of them contributes an unworldliness, and the total unworldliness is just the sum of all of them. So the only way the sum can vanish is if every single term vanishes, and so this contains all the laws of physics. And we can write it down on one line. Now that, of course, is a complete cheat, because although it looks very compact, if you wanted to unfold it, there would be no other way than taking each term one at a time. They have no logical relationship to each other, and unfolding it. The equations of QCD really aren't like that. The different parts of it are related by symmetry. The different colors can be rotated into each other, and that places severe consistency requirements on the different kinds of couplings. And as I said, there are only a couple of non-conceptual elements left, and so it really does describe a lot in terms of a little. Let me skip this in view of the time. So with the quark masses in, we get an accurate theory of atomic nuclei. If we leave the quark masses, the up and down quark masses, to 0, we get an approximate theory, but a very good approximate theory of atomic nuclei. Now, I've told you that the equation is elegant, given you some idea about what's involved. The main question should be, why should you believe me? Is it right, and how can we draw consequences from this? Well, to see if it's right, we have to solve the equations, and that turns out to be quite challenging. This is something I call the big crunch. So let me tell you what's involved in the big crunch. You take something like 10 to the 30th protons and neutrons, hook them together so that they make a bank of parallel computers, run the computers for something like several months, so that's 10 to the 7th seconds, and they run at teraflop rates, which means 10 to the 12th complicated multiplications per second. Don't try that at home. And what are these 10 to the 30th protons and neutrons working so hard for so long doing? Well, they're doing what every single proton and every single neutron does every 10 to the minus 24th seconds. That is, figuring out how to balance the forces between quarks and gluons so as to get the minimum possible energy and make a stable state. So probably our methods of calculation could be improved. They're certainly not nature's way, but they do give us the answer. And here's what it looks like. So first, here's the problem. The observed particles that are supposed to be made out of quarks, and I called this QCD heavy because now I've included not only the up and down quarks, which are important for ordinary matter, but also other quarks so that we have more things to compare. The observed particles that are supposed to be described by quarks and gluons have different masses and different other properties, spins and other properties that I won't go into detail on. And all of these things are supposed to emerge from those simple equations, from those simple with a capital S equations that have only 3 numbers in them. Okay. So we need to measure those 3 numbers, and the most accurate measurement is by fitting to 3 of these masses. So these measurements are used to fix the theory, and now there's nowhere to hide. Okay. Now everything further is purely conceptual, can't be changed. If the calculations are wrong, the theory is wrong. On the other hand, if the calculations look to be right, and the theory can't be changed, and it's close to being right, it has to be exactly right, because you can't change it. Okay. So we fix the parameters, 3 parameters, and now comes the moment of truth. We have to see whether the calculations from this gigantic number crunch agree with experiment, and with a sigh of relief, we see that they do. This, to me, is one of the greatest scientific achievements ever, not just because it uses a beautiful theory to explain a lot of data through very difficult, challenging calculations that press the limits of technology, but because one of these particles, N here stands for nucleon, these are the protons and neutrons, and so this calculation is giving us a first principles fundamental explanation and calculation of how the mass of protons and neutrons, that is more than 99% of our mass and the mass of ordinary matter, arises. We can look inside the computer now, we have faith that it's doing the right thing, to see what our eyes are not capable of seeing. Our eyes were not evolved, or perhaps designed, to see down to distances of order 10 to the minus 14th centimeters, or times as short as 10 to the minus 24 seconds. Those are the relevant times and distances for the things that are going inside protons. But using our minds and aided by the computers, we can calculate and have calculated in the course of calculating the consequences of QCD, what's going on. So here it is. This is the deep structure of reality. This is what's going on. This is what your eyes would see if they were attuned to fundamental physics as opposed to avoiding predators and finding desirable mates and the things we were evolved for. You'd see this kind of lava lamp, which are the fluctuations in gluon field energy. This is calculated. This is not an artist's impression or a lava lamp design. This is the actual calculation that's going on, and this is telling you what's happening all the time in empty space and inside the computer, and also inside the computer as it computes the mass of protons. This is spontaneous quantum activity, also called virtual particles. What is the picture of matter that emerges from this? Well, as I said, you put down quarks, let them settle, let them come into equilibrium with this fluctuating medium. In this picture, I've taken out the fluctuation, so you only see the net disturbance. If you put down 3 quarks, let it settle down, and look at what you get, the energy distribution of what you get, This is our deepest understanding of what a proton is. It's kind of this disturbance in empty space that you get when you plunk down 3 quarks, let them settle down. This is how you calculate the mass and get all the properties. It looks ragged. That's because even with all the computer power I told you about thrown at it, the statistics of this calculation is still limited, so that instead of perfect smooth distributions, which we should have in reality, we still have a lot of noise. So this evolves for a while, settles down. This is, for experts, this is the energy distribution inside a proton, calculated from first principles. And if you add up all this energy and divide by c squared, that's the mass of the proton, coming basically from pure energy. Here's that same thought in an equation. Before, we talked about E equals h nu, the Planck-Einstein-Schrödinger relationship between the energy of a quantum mechanical object and the frequency at which its wave function vibrates. We combine that with what I call Einstein's second law. Einstein's first law is E equals mc squared, but it has a nice corollary, m equals E divided by c squared. Combining those two, we find a unique relationship between the frequency of things we get when we disturb empty space, disturb the vacuum, and let it settle down. So we plunk it, if you like, and let it settle down, see what it does, what tones it emits. And the frequencies of the tones that it emits are what we call and perceive as the masses of particles. And this is not a metaphor. This is how it's actually calculated. So we have a version of music of the spheres in an obviously very strong sense, but there are no spheres. It's the music of empty space. It's a more perfect music that's purely conceptual and yet corresponds to reality. So let me summarize the numerical recipe of the world in the style of a recipe. To prepare normal matter, you need some ingredients. So the ingredients are concepts, the concepts of quantum mechanics and relativity and symmetry, plus 4 ingredients that are not concepts. We need the mass of the electron, the fine structure constant, and the mass of the up and down quarks, and that's all. We cook it in the quantum grid that's boiling like that. Let it settle down, remove, and enjoy. Now, so that's normal matter, and that really does justice to everything one studies in chemistry and biology and biochemistry and material science. In principle, we have the equations for all that. Of course, solving them is a very different matter, but we have the equations. If we look at things on very, very long time scales, or if we look at very, very big things, then new effects, which are weak on short time scales or for small things, come into play. And so to get a complete recipe for the world, as far as we know, we have to add 2 more things. In the category of old stuff, there are weak decays, which take much, much longer than this 10 to the minus 24 seconds, and transformations. This is the subject called the weak interactions, for which Professor Glasgow won the Nobel Prize. And to describe the weak interactions, at least as far as normal matter and astrophysics is concerned, we basically need 1 more constant, the so-called Fermi constant, 1 more non-conceptual element. And then, if we want to describe really big things, we have to put in gravity. Gravity acting between fundamental particles is ridiculously small. The electrical force between a proton and electron is 10 to the 40th, 1 followed by 40 zeros, stronger than the gravitational force. They both go like 1 over r squared, so you can compare them at macroscopic distances, and you'll always get that answer. But gravity, unlike electricity, is always attractive, and so it mounts up for big objects, whereas electricity cancels between positive and negative charges. And eventually, for astrophysics and the large-scale structure of the universe, gravity wins, and we need one more constant to parameterize its strength, and that's Newton's constant of gravity. So now I've done what I promised. I've given you the world's numerical recipe, telling you how many things you have to put in as we have it today. We needed 2 constants, the fine structure constant and the mass of the electron, to get a good theory of atoms and structural chemistry. We needed 2 more constants to do a good job on atomic nuclei and get an accurate theory of normal matter. And then we needed 2 more constants to take account of things that happen over a long time scale or for big objects, 6 constants altogether to do all of practical physics, including astrophysics. So that's pretty good, I hope you'll agree. But 6 is still bigger than 0, so we haven't quite fulfilled Pythagoras' dream of a purely conceptual description. And I've confined myself so far pretty much to normal matter, that is the stuff that's made out of up and down quarks, gluons, photons, and electrons. In the course of studying those things, which are the important components of normal matter, physicists discover many other particles, strange quarks, charm quarks. They have funny names, W bosons. There's plenty of abnormal matter, and we'd like to have a theory also of that. So we have a saying in physics that yesterday's sensation is today's calibration. Now I'd like to describe how we're trying to build on our extraordinarily powerful theory of normal matter to understand the abnormal matter, and also to try to do better on this number 6, bringing it closer to 0. Okay. So to do this, to do both aims, we want to construct a unified theory. A unified theory will have more symmetry, more relationships between the different couplings, and so there will be fewer conceptually independent ones. Also, it will make relationships between the normal matter and the abnormal matter, and perhaps between different kinds of normal matter, and so reduce the number of independent ingredients. Oh, as I said, so the basic ingredients of normal matter are these. We can summarize pictorially what's called the standard model, which includes the electroweak theory and also quantum chromodynamics, really pretty honestly on one page that you could, if you study physics, you can unfold to get the whole theory. Its symmetry group is SU3 cross SU2 cross U1. You have rotations in a 3-dimensional complex space, a 2-dimensional complex space, and a 1-dimensional complex space. And these are implemented by different kinds of gluons, a photon, and the W and Z bosons. So they're very similar kinds of theories conceptually and mathematically. Under these different transformations of symmetry, we get to relate different kinds of things one to the other. As I said, the 3 colors of quarks are necessarily related inside SU3. Similarly, by the transformations of SU2, you relate things in the vertical direction in this picture. And then finally, the strength of the coupling of the photon, or more accurately for experts, something called the hypercharge, is given by these funny numbers on the bottom. And really, this accurately represents the world's numerical recipe as I've outlined it. and someone who knows how to implement these symmetries, how to write down relativistic quantum field theories that implement this structure will always be led to a unique answer based on what you see on this page. So really, that's all there is. This is all you would have to tell the computer. Now, it's remarkably powerful, but you see that it still falls apart. It's still not as beautiful as it could be. It falls apart into different pieces. These are very similar, but in the present state of sure knowledge, unrelated. And similarly here, the different kinds of matter fall into 5 or actually 6 pieces if you count neutrino masses. It's another story, but 6 pieces. Okay, so we'd like to have a theory that combines those 6 disconnected pieces so that they get related to each other, and also that combines the 3 different kinds of symmetry transformations and physically the different gluons and photons and W and Z bosons into a unified description. So schematically, we'd like to make this connection to improve our understanding of the basic structure of matter. Professor Glashow already talked about how constructing this kind of unified theory. The basic idea is to postulate a larger symmetry group, a larger group of transformations that are declared to take one object into another object that has the same physical behavior, thus relating their couplings and relating their properties and unifying the description. If you choose the group SO10, which is mathematically represents the symmetries of rotations in an imaginary 10-dimensional space, and work out the simplest representation, simplest structure into which the quarks and leptons can fall, you find that they click into place in an extraordinarily beautiful way. In this framework, are not independent, but are determined by a precise formula in terms of the color and weak charges. So it all clicks into place. However, it's too good for this world. When we ask the question, is it right, the answer seems to be obviously no. Because if you're going to have symmetry between the different interactions, so that SU3 is really just another rotated version of SU2, so that the different kinds of color charges can all transform into each other and have the same properties, then necessarily the strengths of the different couplings would have to be equal. So the strength of the strong coupling of quarks to their color charges would have to be the same as the coupling of the weak W and Z bosons to their charges, and the same as the coupling of the electric charge, the photon, to electric charge. But in reality, they are not. There's a very good reason why the strong interaction is called strong. It really is stronger than the other interactions. And so if I plot inverse coupling strength, which I do for a reason that'll become apparent in a moment, the strong interaction is on the bottom. The weak interaction fundamentally is actually a bit stronger, and the electric is the weakest. However, remember that when I showed you what empty space really looks like, what we would see if we had eyes that were capable of resolving much shorter distances and times, we saw that it had a lot of structure. Empty space is boiling with these virtual particles. And so when we look at quarks or gluons or the other particles, we don't see them in their raw form. We see them through this medium, which distorts their properties. So if we want to see whether they're fundamentally the same at short distances in themselves, we have to make corrections for the fact that we're seeing them through a distorted medium. Okay? We have to put on our glasses so that we can see things properly. Well, that's difficult to do experimentally, to go to very, very short distances, or equivalently in quantum mechanics, very, very high energies. This is a logarithmic scale, so each of the ticks of this graph is a factor of 10 in energy. The LHC, at the cost of roughly 5 billion euros, will take you from one side of this circle to the other, and then it gets really, really difficult. But fortunately, using our noodles, with the stroke of a pen, we can extend our calculations logically, extend our theories up to much, much higher energies, or equivalently much, much shorter distances, stripping away the distortions introduced by the virtual particles. And this is what happens if you do that for the strong interaction. Okay? The width of this line shows the uncertainty in the experimental determination, and then you can extrapolate to much shorter distances or higher energies. And now you can add in the other interactions to see if they unify. Do they come together, in fact? So take the weak interaction, strip away its distortion, and sure enough, they unify. Now, this might not be as impressive as may not look as impressive as it could be, because two lines do tend to meet in a point. However, it really only looks like two straight lines because I plotted things in this particular way. And also, these lines could have pointed in opposite directions, or the intersection could have happened too soon, and that would have disastrous consequences, like the proton decay that Professor Glashow mentioned. So it really is pretty good that these guys take a long, long time. That is, you have to go to very, very high energies or short distances to see the unification. It could have gone wrong, and so far it looks good. But still, it is true that two straight lines do meet in a point, and so the crucial test comes when we bring in the other interaction. So let's do that. Bring in the third interaction, see if it unifies, and here it comes. Almost, but not quite with the experimental accuracy. Now, if we were followers of Karl Popper, the philosopher of science, we could declare victory at this point, because Sir Karl Popper advised us that our goal in science is to produce falsifiable theories. And here we've produced a theory that's not only falsifiable, but actually false. What could be better? Well, needless to say, that's not our reaction to this. Our reaction is to see, since it almost works, whether we can construct a modification of the ideas, an extension of the ideas. We look for ways to truthify it, make it true, that will make it work, are natural, and change the situation. In our unification so far, we've only considered what it takes to unify the different kinds of charges, and since the different kinds of charges are what distinguish electrons from quarks, we were unifying according to these solid lines, and also photons and gluons. Even if that succeeded, it would have left us with two different worlds, so it wouldn't be a complete unification. And we can ask, is it possible to construct theories that complete the unification? This is, for a physicist, a shocking notion at first, because whereas electrons and quarks in many respects are similar and obey similar equations, electrons and photons, or quarks and gluons, look like terribly different kinds of objects with completely different and contradictory behavior. For one thing, electrons obey the Pauli exclusion principle, which roughly speaking says that electrons don't like to occupy the same quantum state. That is, they don't like to do the same thing or be in the same place with the same energy. Whereas photons, those are called fermions, and photons are just the opposite. Instead of feeling a repulsion when you try to put them in the same state, photons feel an attraction. They like to be in the same state. And that's the principle behind the operation of lasers and the recent discovery of Bose-Einstein condensates and many other famous effects in physics. So they seem to be as different as could be. Nevertheless, in the last few years, physicists found a way of extending the equations of physics we know, not just to have symmetry between different kinds of charges, but to have symmetry between different kinds of spins and different particles that have different kinds of statistics to make connections in this direction. But to get equations that do that, we have to add to the equations we have. We have to make bigger equations. And bigger equations have more solutions, which correspond to more particles, which also corresponds to more virtual particles, which means we have to redo our calculation of the correction due to the fluctuations in empty space to the possible unification. So if we implement this idea called supersymmetry by expanding the equations and see what the new additional stuff does to our dream of unification, we get a lovely surprise. The unification loves Susie. Now it works. And as a bonus, gravity, which started out ridiculously weaker than the other interactions on this scale, now we know how far we should extrapolate it if we are going to get unification, to what energy we should look if we're going to get unification. So we can see if gravity fits on here. If I tried to plot gravity on this, it would differ from the other forces not by a factor of 10 or 20, which these sort of differ mutually from each other, but by that factor of 10 to the 40th I mentioned before. So it would be way, way outside the known universe. Way, 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 way outside the known universe if I wanted to put gravity on this scale in terms of its coupling. And because it's weaker, it would be higher in this plot and out there somewhere. Okay? But we're not asking about gravity as we observe it. We're asking what would gravity look like at very short distances or to objects that had very high energy. And again, with our heads and the stroke of a pen, we can calculate. And here it comes. Gravity, from being way outside the known universe, comes in like that. And does appear, at least roughly, to unify with the other ones. So it's extremely tantalizing that these ideas may be on the right track. If they're correct, I won't do the counting in front of your eyes, but if they're correct, we'll be able to get that number 6 down to 5. That may not sound like a great improvement, but once you've gotten that far, down to 6, each improvement is an epic. And of course, it has much more implications. It brings together the different kinds of abnormal matter into a unified structure. And we understand better why there is that abnormal matter and how it relates to normal matter. So it's tantalizing, but is it true? Well, if you fly over Geneva and look down in the right weather conditions, you can see this kind of beautiful scene with misty clouds, Lake Geneva, the Jura Mountains off in the distance. And then you see this red circle on the ground. Well, of course, you don't really see the red circle, but what this indicates is the path of the great accelerator, LHC, standing for Large Hadron Collider, that's now being completed at the laboratory CERN here, near Geneva. It's roughly 27 kilometers around. It's all underground, so you actually don't see anything from the air. But we can, of course, go down to the ground and look at it. The tunnels are filled with magnets. Everything about it is big. It's our civilization's answer to the pyramids of Egypt, but much, much better, I think, because it's a monument to curiosity as opposed to superstition, and to cooperation as opposed to command. This is one of the major detectors at the LHC. It's called the CMS detector. C stands for compact. This is the smaller detector, the compact muon solenoid, and they're very proud of how small it is. The people who work on this, there are thousands of physicists involved in each of these experiments. Very, very few of them will get Nobel Prizes. They realize they're not going to become super famous by doing this, but they're curious, they're driven, they want to find out, they work very hard, and you can see they become kind of secular saints with halos. Now, it's not just the scale of this that makes it so awesome, but the fact that each piece of it is carefully machined, sometimes with millimeter or micron tolerances to be just right, and it's filled with complicated electronics, so that we'll be able to monitor the results of collisions of protons at enormously high energies, access these high energies and short distances I was talking about to some extent, and figure out what's going on thanks to these elaborate detectors that will examine the explosions that result when the protons collide. This is the Atlas detector before it was filled up with, this is the bigger detector. You get it, here's the human size, before it was filled up with electronics. So this is just the civil engineering of it, so to speak. It gives you, again, a sense of the scale of it. I told you that the insides were complicated and carefully machined. Here you can see the insides, a very small part of the insides of the CMS detector before it was all put together. I don't know who these people are. Thanks to the efforts of these people, we'll find out in the next few years whether these hints about unification that seem so tantalizing have been nature teaching us or nature teasing us. So it's a very exciting time to be a physicist, and thanks for your attention.
Grazie al professor Wilczek per questa magnifica lezione. Volevo sapere, ci sono domande, commenti? C'è qualcuno che vuole?
There are some questions over there.
Sì, lì. Maybe a few words.
Sì, volevo avere un commento da parte sua sulla teoria delle stringhe. Grazie.
Did you get it?
Okay.
She's asking about
The question is about what about the theory of strings? Well, I didn't mention the word strings in this talk, and that's a sign of the fact that you can make these arguments for exciting physics without reference to the idea of strings. Strings are another extension, not inconsistent with the ideas I've mentioned, but adding still more stuff that may be important in the future of physics. However, at present, the string theory is kind of vague, so it's very difficult to draw specific consequences from it. So I tried to focus on more specific things that have consequences we can calculate. One thing I should say about string theory, though, is that I showed you that there's kind of circumstantial evidence, tantalizing hints, that the different interactions might all unify. The strong, the weak, the electromagnetic, and also gravity. We know how to make very specific theories that are very powerful and well-defined for how to unify the strong electromagnetic and weak interactions. When we try to bring gravity into the game in detail, it seems to be much more difficult. And that's where string theory is really promising. It gives ideas for how to bring gravity into the story in a profound way. But at present, as I said, it's still vague, and one can't really draw specific testable consequences from it.
C'è un'altra domanda.
Because gravity is so weak to respect to the other forces,
Yes.
Is there a possibility for the existence of a particle very massive, gigantic, for example, but which doesn't have interactions like electromagnetic or other?
Okay, so
is there the possibility?
Yes, roughly the question is, could there be other interactions that we haven't seen any sign of yet? I mean, because we were kind of lucky to see gravity because it added up.
Only with
Right.
gravitational interaction.
Yes, and that's certainly logically possible. And in extending the laws of physics to make them symmetric, to implement other concepts, theoretical physicists have played with the idea of particles that don't have strong electromagnetic or weak interactions. In fact, one such particle even appears in the SO10 theory, this capital N particle. It went by very fast, and I won't insist on it. But that's a particle that doesn't have strong or electromagnetic or weak interactions. So that's an example of such a particle. And that particle actually plays a constructive role in physics because it gives a nice theory of how neutrinos might get very small masses. So sometimes our equations lead us in directions that experiment wouldn't immediately suggest.
C'è forse un'altra domanda là?
Please, could you tell me something about the Planck particles? About I don't remember which mass, but it's very big. I know.
Yes, the concept I think that you're asking about is the Planck mass. It's not a particle, but a mass. And roughly speaking, it's the mass at which this unification occurs. So actually, I talked about it in terms of an energy, but if you divide by c squared, you get a mass, and that's what's called the Planck mass. More accurately, what people mean when they refer to the Planck mass is the quantity with dimensions of mass that you can form by taking appropriate powers and ratios of three fundamental constants, three honorary numbers, if you like, Newton's constant, Planck's constant, and the speed of light. So, in physics, you may think, conventionally, one thinks one needs units for length, mass, and time, so three quantities. Planck's innovation was to say that you should take those quantities from things that appear in basic physical laws, and he chose the Planck constant, the speed of light, and Newton's constant. And we now think that those were brilliant choices, or at least very suggestive choices, because each of those constants is a conversion factor in a profound physical law. I mentioned quite a bit, actually, about Planck's constant being something that enabled the relationship between energy and frequency and other basic principles of quantum mechanics. the speed of light enables special relativity. In special relativity, you learn that there are transformations that relate space to time, but space is measured in length, time is measured in time, and so you need, and those are different things, so you need a conversion factor to even make sense of the idea that you can transform one into the other, and that's the role of the speed of light in special relativity. And in gravity theory, in the modern theory of gravity, general relativity, the leading idea is that gravity is due to curvature of space and time, and that curvature in space and time is due to the presence of densities of energy and momentum. But densities of energy and momentum have different units from curvature of space and time, so you need a conversion factor, and that's where Newton's constant comes in. So it's tempting to think that in a profound theory that has quantum mechanics, that'll need H, has special relativity, it'll need C, and has general relativity, it'll need Newton's constant, that those will be necessary. You can form a system of units, because you have three things. You can form a length, a mass, and a time. And so those are purely conceptual things. Newton's constant, the speed of light, and Planck's constant. And the ideal Pythagorean program, if we're going to describe, reduce the non-conceptual elements to nothing, to zero, would be to calculate everything about the physical world as multiples of the Planck mass, the thing you can form with dimension as a mass from those three constants, or the things you can form from a length, or the thing that you can form from a time. So maybe that's more than you asked. But the Planck unit has two, the Planck mass has two, to summarize it very briefly, it has two roles. One is that it's something you can construct. It's the only mass you can construct by taking powers and ratios of Newton's constant of gravity, Planck's constant, and the speed of light. And then it has another role which we've discovered, experimentally if you like, that it seems to be the scale at which unification of the different forces occurs.
I thank you, and I just wanted to understand, if it is possible, what's the relation with Planck particles and the space, the 10 space you spoke about. Because it's just one time, or there are many times? That's my...
The 10-dimensional... No. Although people have speculated about more than one dimension of time, those speculations have really never entered the mainstream of physics. Extra dimensions of time lead to paradoxes, which no one has really ever found a way out of. So maybe in the future it'll be an important idea, but so far it hasn't led anywhere promising. The idea of extra spatial dimensions is very popular. In recent speculations about unifying forces, the possibility that extra dimensions exist and that some of the particles are really vibrations in the extra dimensions have become quite popular. At an abstract level, it's already in the standard model and the kind of unified theory I talked about. You can think of these color charges as being labels of a three-dimensional space. And so that's an extra three-dimensional mathematical space that has different kinds of symmetries. So we're very comfortable with the idea of bigger spaces with extra dimensions. But of course, those dimensions are very different from the dimensions that we walk around in everyday life. But nevertheless, it's remarkable that the mathematics we use to describe everyday geometry turns out to be relevant in these very, very advanced speculations about the ultimate nature of reality.
Thank you very much.
Okay.
C'è un'altra domanda qua e una qua. Prego.
apart from Pythagoras' music of a sphere,
Yeah.
and there is another tradition from Hinduism about Shabda Brahman, which means the sound, the original sound, Vedic tradition, from where everything comes from, you know. What do you think about entanglement? I mean, this, how...
Okay, well, in this lecture, although I talked about a lot of things, I couldn't talk about everything. And so I didn't discuss ideas about cosmology, which is what's reminiscent of the original sound. If I were giving a lecture about cosmology, it would be very different in detail, but in some ways the overall message would be very similar. Nowadays we have a cosmology of the universe that we can specify in terms of pure concepts plus just a very few numbers, something like 5 or 6. And that really summarizes everything there is to know about the large-scale structure of the universe. But again, 5 or 6 is still more than 0. And we want to also understand more exotic details of the universe, you know, the detailed fluctuation spectrum of microwave backgrounds and gravity waves, to be specific. And so the details would be very different, but we'd have a similar picture of very impressive knowledge, but also ignorance, and a sort of creative tension between knowing a lot and yet not quite knowing everything. So it's an exciting time in cosmology as well as in fundamental physics. Then another thing I didn't mention that you also asked about is entanglement, and that has to do with, in my mind at least, the creative part of that has to do with trying to use this very strange and powerful theory of matter that we've developed, and in particular quantum mechanics, to do useful tasks. In quantum mechanics teaches us, talking about big dimensional spaces, that to make a proper description, even of relatively small systems, we have to work in something called Hilbert space, which is enormously large. So for instance, if you want to describe 5 spins, just spins, even if they can't move, just spins of electrons that could be up or down, you need a 32-dimensional space. In fact, it's actually a 32-dimensional complex space, so it's 64 real dimensions. So there's a lot of room in Hilbert space, and we've only begun to learn how to navigate, to make our way through this Hilbert space to do useful tasks. The vision that drives a lot of research in this field now is something called a quantum computer that would be attempting to use this extra space, this potentially vast bandwidth, to do useful information processing tasks. Well, although quantum mechanics is about 75 years old or even 80 years old, it's still in many ways a young subject, and I think the engineering part of it is only at the start. So that's yet another lecture. So it's an exciting time to be a physicist 3 times over.
C'era una domanda.
Yes.
Congratulazioni innanzitutto per la sua bellissima lezione. Ora, la mia domanda è più di carattere generale. Lei ha detto che adesso possiamo avere le equazioni per, diciamo, per mettere le basi teoriche della chimica e della biologia. Ora, la mia domanda è questa. Dunque, la nostra mente ha elaborato la matematica, la quale matematica cerca di dare un ordine al mondo fisico esterno, ma la matematica ci può essere utile invece per dare un ordine, come una specie di processo autocatalitico, per dare un ordine alla nostra mente, per cercare di capire i fenomeni così complessi della nostra mente? Grazie.
Okay, so the question is, can mathematics, and I take it you also mean physics, the laws of physics that I describe as the underpinning of which equations to use, can they describe how minds work? And I think the working hypothesis of most scientists who are working on that problem of understanding the mind is that they will be adequate. But there are many things we don't understand yet about how the mind works, and that program is still in its early stages. I should say that it's very important to emphasize that just knowing the equations doesn't mean in any sense that you've solved the problem. Even though we know the equations in principle adequate to describe chemistry, we haven't put the chemists out of business because we can't solve the equations. We need intermediate concepts and creative ideas for how to make useful approximations and figure out how complicated things are going to be explained. So I really dislike, as I think Professor Glashow does, this phrase, theory of everything. It promises much more than we could deliver. We can deliver, in fact, I think very likely we have delivered the equations that in principle are necessary to describe normal matter. And I think brains are normal matter at the end of the day. But new concepts have to emerge to describe what's going on that will make very, very little reference, probably, to the underlying equations. You better get the microphone so that other people can.
Couple of questions.
Okay, we better. Yeah, we have.
It's up to you.
I'm reminded that time is finite here.
Emergency.
Yeah, so we'll just take a couple more.
The emergency of the chaos, even for the deterministic chaos, for example, even for small systems.
Chaos, yes.
What do you think about the possibility to pass from the equations of the quantum mechanics, chromodynamics,
yes.
To the description of a macroscopic thing,
right,
even for small systems?
Right.
Because if in the quantum mechanics systems, is there even the emergency of some phenomena like chaos?
Yes, okay, so the question is the role of chaos in mediating difficulties in relating basic equations to behavior. And, well, chaos is a mathematical phenomenon, that's definitely true, that large classes of equations have a property of being, their solutions have the property of being very, very sensitive to small uncertainties in how you set the initial conditions. It introduces a vast subject, but yes, it is a tremendous barrier to trying to get from the fundamental equations to describing complicated systems and how they evolve over long times. So part of the art of applied mathematics is usually to avoid chaos, to try to focus on things that are immune from chaos. And fortunately, quantum mechanics helps in that regard, because the equations of quantum mechanics are really equations for waves, and they kind of spread out, and they don't have the kind of fine-scale structure that leads to most of the phenomena of chaos. So, for instance, we can make mistakes in the initial conditions of how we start out the quarks when we're trying to make out proton, and they'll still make a very accurate proton when they settle down. It's just because quantum mechanics shields you from a lot of the effects of chaos. In quantum systems, chaos is by no means as damaging or as dramatic as in classical systems. You have to work, you can, but you have to work quite hard to see symptoms of chaos in quantum mechanical systems.
Bene, grazie. Purtroppo il nostro tempo è finito, quindi Ringrazio il professor Wilczek.
Thank you.